All right, so hello everyone. I'm Ian Cohen. I'm a graduate student at UNH working with Mark Lessard. And today I'm going to be talking about ionospheric feedback instability. So a quick review. This was introduced by Jerry Atkinson as a theory to describe the formation of stable arcs. So it's the instability starts with an assumption of conductivity enhancements in the ionosphere. That obviously leads to a change in the electric field. That electric field then maps up into the magnetosphere, where you have a magnetospheric change in electric field. A flux tube that was passing by in the magnetosphere would see a changing electric field, which would generate polarization currents. Those polarization currents would then try to close in field-aligned currents, and that downward current region, or the upward current region, would result in aurora that would make that conductivity enhancement that we assumed at the beginning. So what I've termed as the key observational characteristics of IFI are twofold. There's the low altitude density cavities, and then there's also small scale electromagnetic waves. And we've seen both of these independently in the vicinity of stable arcs, both with the ISCAT radar and by the GEMA magnetic chain. But we've never seen both simultaneously with in situ measurements. So the IFI is basically broken down into two different categories. There's based on the resonant cavity in which it's occurring. So there's the full field line cavity, which happens between the ionosphere and two conjugate hemispheres, so the field line eigenmode. And there's also the Ionospheric Alfvén resonator, which is basically a cavity that's formed by the conducting E layer of the ionosphere at the bottom, and then a gradient in the Alfvén speed at the top. And Streltsov and Lotko in 2008 had a model that showed that IFI occurring inside the Alfvén resonator could generate both of those observational features that I just mentioned. So their model showed two field line currents, one upward and one downward. And it showed that in the downward current region, you would get these small-scale electromagnetic oscillations, mostly on the equatorward side of the downward current region, but extending through most of the downward current region. The idea was that the ponderomotive force combined with transverse ion heating would cause a density cavity depletion at low altitudes, moving that plasma upwards, and then also that would enhance ion outflow. So the idea was we would launch a rocket that would go through at an altitude that would just clip this density enhancement, and we'd hopefully be able to see all of these small-scale electromagnetic oscillations if they did in fact occur. So this was motivation for a 2012 rocket mission, but that rocket actually got scooped. There was a previously launched mission from 2009, which was a two-rocket mission, Aces high and Aces low. And the idea with the intent of this mission was to look at the three-dimensional current closure of the auroral arcs. So we looked at the high rocket, which reached an apogee of about 360 kilometers. And we found some very interesting stuff. So this is a plot of the data from Aces High over about a minute's worth of time. So the top is the all-sky imager from the ground. So here you'll see the enhancement. That's the auroral arc. Here we've got the field-aligned current. So the arc is occurring in the upward current region. Here we have the downward current region immediately adjacent to it. Here we see in that downward current region broadband field-aligned alphanic signatures. That's correlated with very strong, small-scale EM structures that we see here in the electric field. We show electron temperature showing that this is a cold ionosphere, which is one of the stipulations for the Streltsov-Lotko model. And then here we have the HF power spectrogram with the electron density that's derived from that. And here we can see blown up in the fields, we've got those small-scale oscillations that we said were an observational characteristic. And we've also got a density enhancement, which makes sense if we did fly at an altitude that would be in that density enhancement from the plasma being evacuated upward at lower altitudes. So this was the first time that we were able to see in situ both characteristic observations of the IFI inside the Alfvénic resonator. So now you might have noticed, if we go back real fast, the original model from Streltsov and Lotko predicted that these small-scale oscillations would exist throughout most of the downward current region. That's not what we're seeing. We're seeing them mostly near the boundaries of the downward current region. One explanation for that is that the density gradients there would change the Alfvén speed, and that's what would cause the Alfvén signatures at that point. So we went back to Anatoly Streltsov, who was one of the collaborators on this, and presented him with the data and said, doesn't quite match what your model predicted. And he decided that he would go back and do another model where he decoupled the upward and downward current regions. So instead of launching both simultaneously, his new model just launches a downward current region. And you see within about a minute and a half, we get the generation of those small-scale electromagnetic oscillations just on the boundaries. Now, that seems unphysical because we know that the current closure must occur, so there must be an upward and a downward current region. But this model seems to suggest that for at least this process, that current closure doesn't necessarily impact the generation of those small-scale oscillations. So, quick wrap-up. The ACES High rocket got the first in-situ observations of both of the observational characteristics of IFI inside the Alfvén resonator. So that's the small-scale oscillations seen near the boundaries of the downward current region, and then also a density enhancement, which means that we did fly through altitudes where that plasma would be evacuated upwards, causing the low-altitude cavity. And then we developed a new model that decoupled the field-aligned current regions from each other and resulted in something very similar to the data. Now, just one extra thing. I just want to highlight some other work that I'm working on. This is relevant to ion outflow, which we've been talking about for most of the week. We know that soft electron precipitation plays an important role in type 2 ion outflow. And we have a rocket observation from Eric Lund, which showed that there was high electron temperature at altitudes much higher than 1,000 kilometers. And that's interesting because we know that that soft electron precipitation deposits most of its heat down to about 100 or 200 kilometers. So the question is, how does that heat propagate? How does it transfer up from those lower altitudes? And we know very little about it. And one of the things that I'm working on to try to address that question is data model comparison using data from multiple rocket missions to try to address what that transfer of heat could possibly, what that mechanism could be that would be moving that heat up to higher altitudes. So, thank you.
Hi, very good talking. And of course, this is I find this great stuff because, of course, this has been a long awaited to get these observational evidence. As far as the small-scale structuring, though, in addition to the feedback, another mechanism is phase mixing. And if you have evacuated this cavity, that phase mixing is going to happen quite rapidly, which very naturally explains why you would have a lot of small-scale structure right at those gradients.